Hey, good morning, everyone. And thanks, Srini. So it was a wonderful presentation, by the way. We got to see all new features that are coming in. And quite a few of those problems that he already mentioned are working on. We face those problems, by the way. And how do we respond to them is coming later in my presentation. But I'll start with my introduction. I'm Sajid Sayyad. I'm working as the Director of Systems Engineering in Charles Schwab. I've been with Schwab for around 7 years now, and all those 7 years, my main focus is on designing applications for Aerospike and using the basic nature of the key value pair to the ultra-fast, low-latency, high-performing systems. And we have done quite a few things with that already. So today's presentation, what I'm going to cover is a variety of topics, but most of them are focusing on how do we leverage Aerospike, use its potential features, and create a really good, solid business product. So I'm going to start with some of the features that we have learned over the period and how do we actually work and design the systems around. Let me start with our current Aerospike footprint. So if you see here, I'm just presenting in one big picture where we started with a few hundred gigabyte, as Subbu already said in the beginning. We started with a simple POC, loaded few gigabytes worth of data, proved it that yes, we can achieve what we want. And over the period of 7 years, today we have around 171 gigabyte worth of data. We have multiple clusters spanning around 139 nodes. And if you really look at our transaction volume, the per day volume of reads and writes is around 18 billion. So 18 billion reads and writes per day is huge. But what is more important is our peak read and peak write performance. So if you look at it, we have about 17 million records or queries happening per minute. And at the same time, around 16 million is our peak read. So we have a huge amount of data. We have a large number of reads and writes happening. But where Aerospike comes really is the number. So if you look at our read percentile, our read queries are less than 1 millisecond for 99.95% of the times. So only what, 0.035 or 0.04% time, it goes beyond 1 millisecond. So that is about our read. The writes are again impressive. 99.04% is less than 2 milliseconds. And then there is another use case where we don't read on the primary key, where we either do it on a secondary key or issue some scans. Even on that performance, we are less than 4 milliseconds, 99.43% of the times. So these statistics are really great, and that puts us on a very solid platform where we can continue creating Aerospike or continue treating Aerospike as our choice of database for ultra low latency queries. So one of the topic when Srini presented, he said there are some work going on supporting multi-transaction or multi-record transaction. And if we all know, when we design the systems, we want to make sure the system which can provide transaction, either we can provide transactions on the same record when multiple threads are writing, or we need to provide transactional support when the records. Okay. So what we wanted to really do is still have the transaction feature and use the Aerospike's ultra low latency key value performance. How do we do that? Let's say I have one record which is being updated by multiple threads. What is going to happen is you have version 1 of that record, and somebody wants to append something to it, update something to it. You read thread 1 a copy which is, let's say, version 1 of it, then thread 2 reads version 1 as well. But thread 1 and thread 2, when they read it, updated it, and if thread 2 succeeds in writing, you got a latest copy of that data. But thread 1, which has already read the data, and if he updates that or that person updates it, what is going to happen is you're going to lose the updates caused by thread 2. And that is a real stale data problem. How do we avoid it? So we used a feature on the write policy. That is called as the expect gen equal. So there is certain metadata on every record that maintains the generations, how many times the record was updated. So using this metadata, it was a very straightforward. We always know whatever version we read is the same version we updated and going to be persisted. If the data or the metadata does not match, we know it's not a good copy, and then we always have a retry loop where we can read the latest version and then make updates to that. And this ensures we never lose or we never overwrite on a good copy of the data. The second feature is, how do I make sure when the data is not on the same set or on the same record? What if my data model spans the data across multiple sets? So I have set 1, set 2, and set 3, for example. And when a certain trigger happens, I need to update set 1, I need to update set 2, and I need to update set 3. So my set 1 update was successful. My set 2 may be successful. What if my set 3 update failed? At this point, what is going to happen is I'm in an inconsistent state where set 1 got an update, set 2 got an update, but 3 is not. And since we all know Aerospike does not support multi-record or multi-set level transaction, how did we get around with this? So a simple way of capturing a snapshot. So before I update, I take a snapshot of the set 1 record, set 2 record, and set 3 record, and then make sure all my updates are persisted. Once all my updates are persisted on set 1, set 2, set 3, I can signal it saying it is a success, and then I don't really need to do anything with that snapshot. But in the prior example, if set 1 was good, set 2 was good, and set 3 was not, what would I do? I always have a copy, and I always have a metadata. I can go back and replace that metadata or replace that good snapshot. So these are the two techniques. When we employed, what we have achieved is a true system of records replication or a feature where we support around 10,000 writes per second. So that's the massive confidence we received or we created using these two techniques when we employed them together. So I'm not saying we do it like both of them at the same time, depending on the use case, where it spans one set or where it spans multiple sets. And this is how we really achieve the transactions even today. And I'm excited to see what Aerospike is bringing in so that we don't have to do this on our own. There is another feature or another limitation when we talk about the record size. When we try to create the records up to version 4 or 4.2 to be precise, we had a maximum record that can go up to 1 MB. And around version 4.2 later than that, we had up to 8 MB. So it doesn't really matter you have 1 MB, you have 8 MB, you are still confined to a particular record size limit. And we know there are instances where we cannot fit a particular use case in that 1 or 8 MB limit. So we need to be really creative to find out how do we come across. So if you look at our regular relational database, we can create multiple tables which are correlated by a certain key combination. And then you can easily spread out data, and your record size limitation doesn't come that evident. Aerospike supports you a very good feature where we denormalize it. And in the denormalization, what we do is we take multiple tables, rearrange them, and try to put them in a flattened kind of a structure. And I'm going to talk about what is our best case for denormalization is. So when you denormalize, try to put multiple tables into one, what tends to happen is the size keeps growing. And you easily go beyond that limit. It could be 1 MB, could be 8 MB. It rarely happens that all of your records are going beyond that limit. So even if you achieve that 90-95 percentile use case where all of your records are under the limit, there are still certain use cases where your records are growing beyond that. So what do we do in that situation? You cannot say that, oh, by the way, I'll have set 1 where all my records follow this pattern, and set 2 where I have a totally different pattern. It doesn't work that way, because then it creates complications for the developers, and it creates complication for further enhancements. So what do we do about that? So we created 2 homegrown solutions. Solution 1, where we know a certain bin that will grow over the period of time and cause the entire record to breach its limit. So in that situation, what we did is we created an extension that can actually span, that can actually split that bin across multiple child records. And this way, we will always have a way to grow that particular bin beyond that limit, infinitely if you really want. Again, infinitely is in theory. Do we really put it in practical? Yes, I have certain bins growing up to 150 MB. So I can grow that up to 150 MB, 200 MB without any problem. The only reason here is, or the only limitation here is, when I split that bin, I still have to restitch it together. So if it is spanning across, let's say, 10 records, 10 1 MB sections, I still have to stitch them together and then return it back. So that adds a little complexity, but for the developer, it is the same read operation, same write operation, all the splitting, all the joining back that happens in one reusable library that we have developed. There is another use case where not one bin, but more than one bin could span and cause the record size to grow. So what do we do in that situation? So here I cannot pinpoint one bin and make it grow beyond that limit. So in that situation, we created a way where we can splice the entire record. So not the single bin, but take the full record. Let's say I know up to 300 items I can put it in, and up to 300 item I don't have a problem. It still stays within my limit. But 301st item starts breaking it. So when that situation comes in, again we have this homegrown utility. What it does, you give them 1,000 records, and it will batch it in terms of 300 or 400 or 500, whatever is your predefined limit. That still keeps it within your 1 MB or 8 MB limit. And when we do this, we store a particular record metadata. Because see, now I know there are 5,000 records when I write it. How would I know when I'm reading it, the 5,000 are coming back? So to know that, we add a certain metadata. And that metadata helps us track it. That, oh, by the way, this one particular primary key is not just one record. It spans across 5. So when I read it, I read 1, 2, 3, 4, 5, stitch it together, and then use it as one record. So these are the two ways where we actually overcome the limitation of record size by doing the splitting of one bin or slicing the entire record, and with the help of a metadata. Now, the next item I'm going to talk about is what are the different ways we learned across doing the data designing or data modeling. So we all know we have worked with relational database for years and years, and every time we start with relational database, one thing comes into the mind: do the normalization. Because in the old world of relational databases, we were taught to have no redundancy or minimum redundancy as much as possible. And how do we achieve? We do the first form of normalization, second form, third form, or whatever form we go. The way we do is create smaller tables, create individual tables, have the primary key and foreign key relationship, and this way you can easily separate your data. You can always span your queries by doing multiple joins and get your data back. The very important consideration here is we are no longer in the relational world. So when we go to this NoSQL world, we have to come up with a totally different data model. That data model suits our query pattern. How am I going to query the data? Do I need this data? What I see here, I have taken a simple example of an employee working in a particular company, and an employee going through certain trainings, the employee going through certain review process. So if I look at this particular use case, what strikes me more? Am I looking for a certain department? Am I looking for a certain training? No. So if I look at this example, what I'm querying about is an employee. So you can query about a product, right? You can query about a certain service. So I have taken this example to showcase when it comes to data modeling, the very first thing we should worry about is, what is my use case? What is my query pattern? Because once I understand the query pattern, designing for it, it becomes even simpler. But if I don't understand my data, if I don't understand how the data is coming in, and I don't understand how the data will be taken out, the design suffers in the later years. And ask me, we have done that. So we have designed in a certain way and overlooking a fact that it may not be used, and come next year, people want to get the data that way. So it is very essential to understand what your data is, how the data is coming in, how frequently the data is coming in, but more so important is who is going to read the data. And when you're reading the data, do you need the data on a primary key? Do you need the data on a secondary key? All those things becomes really, really important. So when I'm looking at this data, let's see in an Aerospike world, how would I actually turn this relational SQL model into a non-relational or a flattened, denormalized schema. So as I said, and don't worry about all the text if you cannot see. I'll try to talk through them. Can you read in the back, at least the table, not the text? No. Can we zoom in a little bit, at least on that? Is that even possible? Just the top table maybe? Don't worry about the list. Don't worry about this thing, but the table. Can we zoom in? No? Okay, never mind. I'm sorry, but I'll try to talk through it. So don't worry too much about what is there on the screen then. So initially what I talked about is, I have a certain number of tables which were represented as a relational model. And there were multiple tables, like an employee table, an employee's department table, an employee's job duties, and then I have employees' performance reviews and employees' trainings. So having those many tables, I always have to store them differently and I have to query them differently. But my central aspect is always an employee, right? I want to know employee 1 or employee A. So anything about that particular employee, so my central theme here is about the employee. So when I created this denormalized or flattened out NoSQL schema, the first thing I did is I kept employee ID as the primary key because I want to know everything about that employee. Then what I did is created those bins with information like all about the employee's information, like the first name, last name, date of birth, or whatever that is, it becomes one bin. It goes as a complex structure because all that information, right? Employee's name, employee's date of birth, employee's whatever that other qualifying feature, it becomes multi-field. And how do I store it? I store it simply as a blob or a binary large object. I can have an object and serialize it as a byte array and store it. So that becomes one bin. Then I store employee's department information, which department it works for, what is that location, how far it's located, and all those things. I store employee's job details. What are the job aspects of that employee? The other table we saw, right? The job table. I store that as one bin. I store the performance review and employee's training. So all those different values that were stored in different records in a relational database, what I do now, I store them as one bin. That bin is now compressed as a binary serialized data. And on top of that, what use cases I'm going to support is if I want to know anything about that employee, I need to know the employee ID. If I have an employee ID, I get all those information in multiple bins. But today, I have an option when I split it into different bins. I'm not interested in employees' training history. I'm not interested in employees' performance review. They're on different bins. If I don't want, I don't query. So I can still have some segmentation, right? But I have an option to retrieve everything if I need in one go. So I can satisfy the query pattern, and I can still pick and choose what amount of information I want to read. And if I can read very well, I can go and update that as well. So that still gives me this feature. Now, if I don't want to query on employee itself, if I want to know what are my employees who all work in San Francisco, or tell me all of those employees who work in, say, sales. If I do not design for it, that becomes a problem. So how do I get around that one? So you see, I have a choice of primary key as employee ID. At the same time, what I can do is I can extract out certain features from those blobs that are there, like employee details or department details or job details. What I can do is, if they are binary serialized, there is no way I can peek through them. So if I really want to know that I want to know all my employees in a certain department or a certain location, or having a certain rating for that matter, right? What I can do is I can extract those features out of the blobs and put them on their individual bins. So I'm not sure if you can read here, but I have a certain section for secondary keys. And in that secondary keys, what I have actually created is I have extracted out the employee's location or employee's department as individual bins. And then I can index them. And when I create a secondary index on those fields, I can always run the queries. And this is very important when I said I need to understand my use cases. If I did not know that this is my use case, I want to know employees working in a certain location or a certain department, then what I need to do is I need to go modify my schema, take those bin information out, and create an index. So if you look at this particular data model, it gives you a very fast read-write, because you can compress the data, you can have everything collected together, but then it still limits you from a future use case because your details are packed into blobs or binary arrays, and peeking through blobs is not possible. And this is the real limitation we faced. So in the beginning, we were so very excited to create the bins and serialize them in the blobs, and as we progressed, what we realized? Everything good, but now we are limited. Unless we go, reverse engineer the schema, extract certain bins out, and then spend through those development cycles. It causes us so much time. It causes us so much development cycle. So what do? So for this particular problem was answered in our second schema or second way of creating the schema. And we call it now the Aerospike optimized model. So how do we get around the problems? The very first thing is avoid blobs. Because once you serialize anything, you cannot do your granular queries. You cannot, in fact, look into your blobs. So the one thing we have learned over the years is no more blobs, no more binary serialization. And if you cannot do binary serialization, how do you still get the data, still achieve the denormalization, but collect the data that can be readable, that can be fine-grained updated or fine-grained queried? For that, we are using the lists and maps. And lists and maps came to our rescue like the best part of it. So if you, I know you cannot correlate those right now, but in the earlier schema, I had all the employee details, job details, the department details, and the performance reviews and training history, everything as individual serialized blobs. What I'm going to do with that now is, rather than storing it into blobs, you see everything here is either a list of native data type, like list of integers, list of strings, or dictionaries, the maps of integers, maps of strings, or maps of, I mean, I can go any level of nesting if I really want. So what I actually did is, I opened up the schema. I still kept one primary key of employee ID. I can still create multiple secondary keys based on my use case. But with this approach, I still have, you see here, the employee dates. Earlier, the employee's joining date, employee's birth date, there were employee's name, all those were in a blob serialized format. What I did, I opened them up, and here I simply created employee's first name as a native bin, employee's last name as a native bin. I don't have to pack it again into a blob. And then I created simple bins like employee's gender, employee's dates, and dates become now a list of integers. Now you ask me, how do I store date as integer? I can simply convert that into longs or ticks or whatever, right? In epoch number, if you really say. But those things are now a map with a key as a string. That key tells me it's a joining date or a birth date, followed by an actual value. How do I make this extendable? Because it's a map, right? Today, I created only the joining date and birth date. What if I want to know when my employee was separated, when he left the company? Do I have to do anything to the schema? Not really. It's an open map. I can always create one more key value pair inside that and say date of leaving or the date of resignation and add one more value to it. Do I have to go through that lengthy cycle of development again? Do I have to modify anything? Not really. It's simple map operation. You add one key at the date of leaving and the actual value when the employee left. So using this particular feature, one thing I get is I can always extend. I can always enhance without doing too much of a development cycle. Same thing I did with the addresses, I did with the job details, I did with the performance reviews. If you see the performance reviews and job details, now they are complex, even complex structure. It's not just the map of a plain value. It's a map where the key is integer and the value is a list of strings. So I can be very creative. Not just one level, but I can go level deep, 2 levels, 3 levels, 4 levels. And one thing I think Piyush is going to cover right after that is how do I use expressions to query those. So it is stored as a native value, which means I get an ability to look through those. And this is the best feature. We combining the lists and maps along with expression to achieve the query pattern that we wanted. And we didn't have to plan from day one for this. As we go forward, we can figure out, we can write the queries and still get the data at the same speed, at the same performance. In the old ways, when we created those blob, it was good for speed. It wasn't that good for extending the current solution. And you know what? The bigger problem than that? If you read the data on AQL, what all you see is zeros and ones, all the binary characters. Then you have to write special tools to read the data, convert that from binary to your presentation format, and then show on screen. But if I store in native format, I don't have to write any more tools. I can simply use AQL or any other tool that peek through the data and show it on screen. So that saves you from building those manual tools or custom tools. So that's the reason this optimized model solves so much of our problem and still gives you the same performance benefits. The next one I'm going to talk about is, how do I still ensure all my data is good quality, the data is isolated, and the data is not impacted by any of my either zone failure or a rogue program going and creating or corrupting the data. So a very simple zone isolation strategy we are following, and I'm going to show it in two parts. How do I make sure when I write the data, it is still all the copies are good, the data is not corrupted, and the data is still highly available. So we divided our whole architecture into two regions, as everybody knows. In fact, it's not two regions, but I'm showing, for example, here two regions. So I have a primary region, and then I have a DR region. So in the primary region, what we did is we created two zones, Zone 1 and Zone 2. And in those Zone 1 and Zone 2, we created individual Aerospike clusters. So if you see here, you'll see 4 Aerospike cluster 1, 2, 3, 4. They're in fact spanned across multiple networking core. So they are rack aware. So internally, there are actually 8 clusters. So on Zone 1, I have network core 1 and network core 2. So my rack aware cluster is spanning across 2 network cores, but for outside world, it is just 1 cluster. And same thing is across all zones. So in this architecture, what we do is we have a system of record. We get the data in different format. And I'm showing you just NAS because that is showing you the flat files. But I get data through messaging for near real-time updates, right? Whatever type of data that is coming in, that data comes to every individual zone, and the data is actually parsed and written into Aerospike. If you see, all of those happen in parallel, which means I maintain all my Aerospikes in isolation. The Aerospikes are not talking to each other. I'm not using XDR. And there are reasons. We are using XDR in certain use cases, but XDR is not used globally across all our databases. So we are using XDR only on need basis, but most of the times our replication is manual. Why did we choose it, by the way? So if you go to the last line, you'll realize there are 2 more labels, stable label and the latest. So imagine today I released version 1.0 that writes the data, and I released it to across all my writing application. You can always have that, right? Or you can have a blue and a green copy. So application blue-green is very easy to manage. But when that application starts writing to the database, what will happen? If I have XDR across, and for whatever reason, one of the element is not writing the data as expected, it will start replicating across all remaining copies of the data. And that will create big troubles for me. So the first thing what we did is, we isolated our Aerospikes so they do not XDR replicate. Even when they do not XDR replicate, I do not deploy all my application versions all at the same time. So even in my primary region, all my writing application are first deployed to, let's say, zone 2, which shows my latest copy. So if zone 2 is writing the data, and it's not writing the data in the way I expected, let's say it starts writing the data and starts corrupting it, what do I have to lose? I don't have to worry too much about it. I'll just take the entire zone out, and I still have a good copy of data from my zone 1. So zone 1 is always stable. Zone 1 always has my good copy of the data. And if the latest copy of application is not writing the data in expected format, I can still isolate my customer's impact from that. So that's the reason I'm always mentioning or maintaining zone 1 and zone 2. And DR is the same thing. I don't always deploy it to DR that way. Imagine my application version now deployed to zone 2. It is going through my robust validation cycle. All the cycles are completed successfully. I stayed there for a few days. I made sure all the data looks good. Then what I can do, I can simply put it back in. And that way I can increase my availability or capacity there. I don't have to worry too much about it. And that gives me the confidence, that gives me the peace of mind that yes, any new, either the file format that is coming in or any new application version that is coming in, I'm always confident that it's not going to corrupt the data or not going to cause widespread impact to my customers. So having different regions, having different zones which don't talk to each other and still maintain the latest and the stable copy, that gives us the confidence. Now, when this write is happening, how my applications know? How do they know that, oh, by the way, I should read from zone 1 or I should read from zone 1 and zone 2? So for that, we have to go to the next slide and see how do we maintain that. So from the consumer perspective, what you see is the consumers come in, they come into a load balancer, and a load balancer is very straightforward. It tells you which Aerospike to connect to. Okay? So in the normal scenario, when my applications are all healthy, the load balancer can put you either on the stable zone or can put you on the other latest zone. But let's say I have a catastrophic problem in my application that started corrupting my zone 2, right? That is my latest copy. What the load balancer will do? It will stop directing connection, or it will stop the applications connecting to the second Aerospike, which means on my connection layer, the consuming applications don't really worry about where to connect and where to get the data from. For them, they always come in, they always see where is my load balance, and that load balancer tells me connect to Aerospike 1 or Aerospike 2. Or in fact, if I am in a DR exercise or something happened to my primary region, it simply drops it there and starts directing to one of the zone in DR or both of the zone in DR, depending on how my current situation is. So this way, I don't have like applications trying to figure out, am I healthy? Am I in a problem? Should I connect to zone 1 in primary region? Should I connect to zone 2 in primary region? All those logic is taken outside of the client application. And the only thing they worry about is, tell me where should I connect? And that part is giving us the confidence where we don't have to micromanage every application and we don't have to spend hours in case of a zone failure or in case of a full data center failure. It is a matter of configuration, and the load balancer itself knows where to start diverting the traffic. Okay, and after this one, I am at my last slide, which talks about developers. So far what we have talked about is the architects, the data architects, the solution architects, the network architects. Now the last part is very important. if I am a developer, what are my best practices? What should I keep in mind when I'm developing applications for Aerospike or consuming data from Aerospike? So again, it was a huge list. I have to just compress in one slide and choose my top 4 or 5 items. What am I going to use as a developer to get the best features out of Aerospike? So the very first feature is, if I'm writing a client application, we all know there are concepts of connection pooling, and people say start creating connection and dispose them if you don't need. The best practice we have learned across is create one long-running connection for your application. Do not dispose it. The client, what we use is a C# client. The client is thread safe. So you can use the same client instance for multiple threads if you want, and it will still perform best. So the first and foremost thing is, do not spin multiple connections. What we have learned is there is an impact, not on a small case. We still have about 80,000 connections, right, Karthik? Yeah, 80 to 100,000 connections come in, and we don't have any problem. We can still have multiple connections, but what we find out best is have one long-running connection per the application lifecycle per cluster. So if you have 5 clusters, create one connection per each cluster. But don't keep creating connections per operations. So if your method 1 comes in, it needs data, create a connection, destroy connection, don't do that. That doesn't work well. Second thing we have learned is, it's very important with the policies. Any operation that we perform, whether it's a read operation, write operation, or the batch read, or the scan operation, it has to supply certain policies. So never apply the policies by like saying null policies. So we tend to say null works best, I'll pass null. So that still works. Then what's the difference between a null policy versus a policy that you impose? So policies have certain defaults. Like you can have an operation timeout, a socket timeout, a number of retry that you can do with it, right? So every time we create that operation, we want to make sure the policies are imposed. So what we do, when we create the connection, we create certain defaults. Like this must be number of retry, this must be number of millisecond before it does a retry or gives up the connection. So all those things we created into a configuration. When we create a connection, use those values and instantiate those policy level defaults. So once those policy level defaults are added, what do we do next? Create the policies on the fly. So if I want a write policy, I can always say get me a client.write policy default. That gives me all the defaults that I've already configured. And then override whatever is required. So override your generation policy. If you want to make gen equal, you can always do that. But then you don't have to set all your timeouts all the time over and over, right? So if I want to make sure a certain feature is there, I can always add, but I don't have to default that feature all the time. So you have your connection created once, you put all the defaults in there, and after that, you can override whatever is needed for that operation. And that gives you the best tuned performance. The other feature we have found very useful is the write retries. So what used to happen in very early days, we have a record that we want to write, we want to persist. We do client.put, and then if there is a network blip, the write operation does not work. What happens? We catch the exception and say, oh, the record did not persist, and then move on. People will know there is an exception, but then what had happened? I missed the record. My record is in inconsistent state because I expected that to be there in Aerospike. It's not there anymore. And then getting that data back from the system of record, syncing it back, it was a huge manual cycle. How did we get around it? Simple settings again on the policy. There are two very important settings: maximum retries and sleep between retry. The values is by default 0. And that's when I said don't use the default values if you want to make sure your application is performing robustly. So what I do, I always set this max retries to 3, which means if my first put operation is not able to persist, what will happen? It will wait for a certain millisecond, whatever you have configured, sleep between retry. Let's say you mentioned there 10 millisecond or 20 millisecond. So the operation will be retried again, second time. If it didn't work, what will happen? You will wait for 10 or 20 more milliseconds and then do another retry. So at least I get 2 or 3 chances to make sure I do not lose the data. And that happens internally. I don't have to do anything for it. Just set the appropriate defaults or appropriate property values on it. The other important feature we have learned across is when we want to store the data the way we want to retrieve it. We do not want to compute the values over and over during the read time. So imagine I have a record that is read like 10,000 times a second, and all consumers wants to add 3 values, right? Why do I let those people do that calculation? Why not I pre-compute the values and store it in Aerospike itself? So those compute are saved on the runtime. So another thing what we have learned is, do not get the data, do the performance later on if it is used multiple times. So what we do is, we pre-compute the data and store it in Aerospike. And again, somebody might think it is redundant. Why do I do it? Why do I waste some space there? But then when you compare that in thousands of times a second, you always gain a lot of performance throughput because of that. So another best practice we have seen is always do your pre-computation. That pre-computation may not matter too much when you are writing, because at write time it is additional maybe a few microseconds here and there. But when you do that performance, when you read that record over and over, 10,000 times or 20,000 or 50,000 times a second, you get the value out of it. And last but not least, and again, Piyush will talk about in detail, what we have found is expression filters do a tremendous job of doing the filtration on the server itself. In the old days, when the predicates or expressions were not popular, what we used to do is, we used to get the data based out of a secondary key. And that would give you maybe 10,000 records. And out of those 10,000 records, we would go one by one, filter out, and get only 10 records out of it. But then what had happened through it is, you still transmitted 10,000 records over the wire from the server. You performed your filter and finally used only 10 records. And over the years, the predicate filter and now expression filter, that had improved so much that you can always say, by the way, do all this filtration on the server and give me only 10 records. And that improves your time over the wire or your individual application logic to just throw out everything that you don't need and get only those 10 records. So expression filter is one thing that helped us a lot. And expression filter, again, a word of caution. Do the expression filter only on either the metadata queries, or do the expression filter on results of secondary index. If you just run the expression filter by itself, what you're causing is a scan. And I have learned that hard way. So don't repeat that mistake. Make sure the expression filter happen either on the result of a metadata or the secondary index. And that was the last point. Thank you.